Hello YouTubers, welcome to my channel Gate Logic. In this video I'll share a major milestone with you. I'm very happy to share this with you, and as you can see that there's some flashing lights, there's motor. So basically this is turning very slowly right now, and right here I have a display that shows a frequency at which this light is flashing and the output to the motor that you see it's turning very slowly. This one thing I want to say that this step has cost me the most in terms of time, and this has delayed my project probably good a month. But I have learned a lot in this project, and definitely will be able to apply this in future. So without further ado, let's begin. Okay, so this is the hardware introduction. So I want to explain exactly what kind of hardware I'm using. Starting with the motor, has nice and clean specs. This is a NEMA 17 stepper motor. It's rated for 24 volts. Doesn't say on this label, but on its spec sheet, I have it laying about here. Let me see. Let's put it down. Here's the spec sheet, and this is a down here. There you go. Okay. So this is a 24 volt motor. It can take 1.8 degree per step, and it takes about 1.5 amps of current. Pole orientation, as you can see, A and B orientation. Although I feel like the coloring, the wire coloring, I have to check that. I am not intending to use this in my project. This is testing and display purposes. And this just gives us a little bit more information on the step sequence that the drive is taking, basically for each step. It's energizing black, then red, the first step right here, and then for the second step, red and green, and then the third step, it's energizing green and blue, and so on. The cycle goes on. So that's how the stepping works in stepper motor. So yeah, there you go. NEMA 17. I'm using this with 12 volts. Yeah, I'm using this with 12 volts. The motor is rated for 24. 12 volts work on this. Obviously less voltage, less amps, less power. So that's my intention. Save power as much as I can overall, so my system can perform longer on small amount of power. So that's one thing. Let's focus on the second device here. This is our DRV 8824. This is basically driving the current at every step that I'm sending it on this pin right here that I'm trying to show it. Let me zoom in a little bit. Let's see if this is more visible. Yeah, okay. A little bit better. Okay. So I'm sending step on this pin, and it then controls the current output on these pins, the blue wire and the yellow that you see in the view. Overall, this is the pin configuration. The gray enable M0 and 1, 2. These pins you don't have to configure if you are just testing. In my case, they're not configured as such. They don't need to be. I can remove. As you can see, I had one pin configured. I believe it's M0 I had configured. I don't need to. The motor will still work. And let's zoom out to show you. Yeah, the motor still works. The visible change that you'll see as I plug it in, it will slow down. It's still moving, as it's not as noisy as it was because the step resolution is changed. There you go. So that's the left, starting from the top of the chip. I have the chip separated in my hand as well. So let's see if I can get it close to my camera. Okay, so the pins. This is the pins I'm talking about from the left side top here. This is the enable, and then the three pins M012 after that. And let's see, let me put this here. What else? Then we have reset, sleep, step, and direction. Reset, sleep, you have to set them to high. You can connect to your controller if you further program your logic to control these aspects of this drive. So reset, I haven't really experimented with this pin. Sleep, I understand that probably stops the motor for a while and prevents the current flow. Enable, disable obviously prevents the motor from moving, and I believe when that's the case, the coils are still energized to keep the motor in place, so it doesn't move. So whatever it's attached to doesn't move. All right. Overall, the left side is connected to your microcontroller. The right side is connected to your motor. And you can see that from the right side top, the first two pins are power and ground. Then the coils, B1, B2, A1, A2, and again the faults and the ground. The last ground on the right side is actually your microcontroller ground. So basically for your signals, you want to provide a ground. Further, actually, I'm thinking maybe I should introduce a isolation between these two. There may be a quality issue in this. Maybe there at some point the motor will push the current through the chip. At some point, it can happen. So I'm thinking maybe I should have a isolation uh, barrier between the two. I'll figure that out, and in later iteration you'll see that in place. Alright, third component in the view, this is a capacitor. I'm using a 100 microfarad capacitor, and this is a polarized capacitor, meaning that you will see a plus and minus sign on these capacitors. Let me twist it a bit. Let's see if I can get a good view of that capacitor as well. Ooh, that is a good view. Okay, polarized capacitor. They usually have a gray marking on one side indicating the negative, and the other pin is obviously the positive. So they have to be oriented the right way. Negative has to go to the negative, positive has to go to the positive has to go to the positive. And it's essentially what I understand, that this basically is smoothing the input, the power input for the motor, because obviously power, as the stepper motor is going through its steps, the overall power input will need to be smoothed out because it's influencing the input as well. So the capacitor is needed for that, and then I have a simple multimeter. Let's zoom out a little bit more. Simple multimeter to observe the frequency changes at the step inputs, and you can see that I have a C++ code running on the HPS. It's incrementing the counter, and the step here increments, and you can see this frequency change of every step. So that is the hardware setup. Okay, let's get to our HPS Linux image. So for all this to function, we need a Linux environment, and the Linux environment is already prepared by Terrasic for us. If you go to their website, you can browse to the DE10 boards, DE boards, and there are a number of them. Ours is DE10-nano. So I'll browse this down. There's a DE0-nano as well. And here's our board. Click on resources. And the first one that you see here is the SD card image. Now, overall, all the images will boot. There are actually 3 images Terrasic is providing. They will boot. Each one is built with slightly more desktop environment, slightly more volume basically. And you can run a web server if you like on this SD card image. It's that built well. However, not every image has all the options included by default. You can add them in later, but by default, not every image has all the features. And this I found out from experiment, trial and error, basically. So this SD card image, this one particularly that I highlighted, this one is Angstrom, I believe. And this one has the desktop Debian environment. However, it did not work for me. What I was trying to do was basically access the lightweight memory and access it from the HPS and try to write to the FPGA and then trying to read from the FPGA side. Did not work. Did not work for me. As a matter of fact, the point where the HPS tries to load the image into the FPGA environment in this MCell. Well, my video is a bit frozen right now. I'm gonna disconnect it. But anyways, as I explained earlier, the MCell switch configuration set to 0. This image did not work with that configuration. There's a FPGA manager that the Linux kernel is configured to run, and there's a DTB file that accompanied with it to allow FPGA or the HPS, one or the other, to write at the right locations. They initiate the FPGA manager, and an FPGA manager in that pin configuration did not function. So I had to eventually abandon that. So part 3 of the video or of this project that you will probably have seen. If you have seen it, if you haven't seen it, please go and view that, because there are some pieces that I did talk about that we will apply later on. But right now in this part 4, I'm using a different image. I'm using another image that you will find if you scroll down here, somewhere here. Yeah. So I will be using this LXDE desktop kernel 4.5. The XFCE and the console again did not work for me. So I wasn't sure what was going on. I tried to generate a DTB file. I tried to generate a kernel, Linux kernel from SOC FPGA folder that Terrasic also provides, but did not work for me. So I'm stuck to this LXD right now. However, in the next few more parts, I will come back to this, and I plan to modify the DTB file and modify the kernel and make that work with my configuration. For now, I want to document this step. I want to share this with you, and then develop the large scale, basically scale out from this baseline into the larger portion where I can control the 3 motors simultaneously and without any errors, and control them through the HPS. One other piece that I want to share: when you will research online, you will also come across this Zhangman site. Let me see if I've saved this. Yeah, here it is. So it's on GitHub, Zhangman D10-nano. Very helpful. It was very, very helpful. I must say that it helped me understand exactly the role of the DTB file and what to do when you're developing your own SD image, which I did generate one on my own, but it wasn't complete. The image I acquired was, or the files that I acquired for the image were incomplete for the functions that I wanted to have in my Linux image. So that I had to abandon and go back to the Terrasic image. However, it is doable. It is creating the image to the point where the Linux boot, that portion did work, and so it is something doable that if I put in full time, maybe I will be able to get it going eventually. But I want to focus on getting this project complete and done and test my hardware with it. So uh, that's basically what I want to say at this point, and I don't want to get into further details of exactly what this site. In short, what you want to know about the DTB file and the Linux kernel is that the DTB file is a configuration file that Linux kernel read in order to prepare the hardware before the FPGA. It's basically a binary file that you will compile, and the compilation is basically from a bunch of other DTSI and DTS files that eventually give us a DTB file in a binary format, and we can put it in the same FAT folder the HPS would read from upon boot. All right, coming back to our Terrasic website. So I download this LXDE desktop SD image already. I have it on my drive. Let me see if I can pull that up. And I've already unzipped this. Here's our image. So what I will do is prepare our SD card. Let me see if I get my camera going again. And no, it's still frozen. Okay, we are back. And let's see, let me zoom out a little bit so I can show you. I'm plugging in my SD card. So I have a micro SD card already prepared. It does have a image, an older image that I was testing, but I can rewrite this. Let me show you what the image looks like. So I'm going to plug it into my laptop. And let's see what's in there. So the LXDE, XFCE, the Angstorm, all these SD card images will have a FAT partition. The FAT partition will be the placeholder where you will keep your DTB file. This is your FPGA binary file that the HPS will use to program your FPGA on boot. I'm surprised I said that in one breath. So SoC system RBF, we will generate this when we get to the point where we program the FPGA and convert the output of the FPGA compilation into the RBF. So okay, so that's one thing you want to know. Another thing, if you plan to modify the DTB file, you will have to keep in mind that the Linux kernel, the kernel file, which is this zimage file, you will also have to generate that, and that must match the DTB configuration. Otherwise, if there's a even single bit of mismatch, What I mean by that is, let's say you want to enable HDMI. You enable it in the kernel, but you don't do it in the DTB, or you don't do it correctly in the DTB. The image will not boot. Basically, that's what would happen. That's what's going to happen when you hook up to your console, and you will find out that the Linux isn't going anywhere. It's not going to the point where you can log in and do anything. So that's just I wanted to give you a little heads up, and you're gonna hear these heads up all the way along this video. So just keep your ears open. One other thing I want to mention, that I am going to use my disk tool. Basically, it's this, and here's my SD card. You can see there's some free space in there. So I'm going to use this tool. However, if you are more used to the terminal, you can use the DT command. Let me see if I can pull something up. That there's a DD command that you can use. Basically takes it's just another tool to flash or back up your disk image. It's a very, you may want to learn about this one. This is a very helpful command if you want to do live backups. It does it without disturbing the OS, and it does it very well. So this is one other tool in Linux. You can also use gpart. I also have that. Gparted. Takes some time to open. Looks like this. So you can also use that. It's a very nice tool as well. If you are working in Windows, you can use a tool called Balena Etcher. Let's see if I can search that up. Yeah, there you go. Flash OS images. So just get this tool, it'll do the same job. So no difference there. And all you have to do is point to the file, point to your SD card, and it'll do the rest. Okay, let's come back. I'm selecting my SD card, and we will flash this. The option I'm using is restore disk image. I will browse to my image. This is another one of the images. This is not the LXDE, but so let's find our LXDE image, and we will restore. And the target is busy for some reason. Let me see if I have the, oh yeah. Let me eject. Okay, let's try again. We'll come back to it once this image is, the restoration is complete. Okay, so our SD image is complete. As you can see, there's some additional space here. I can utilize that. And what I want to do is extend this image. So this is basically where the Linux is residing. This is the FAT or FAT partition that is holding the RBF file, the DDB, and the Linux kernel image. So what I want to do is extend this Linux, because maybe in the future I want to install more programs, and just this 3.3 gigabyte capacity or the range isn't going to be enough. I just like to use the full capacity of my SD card. So let's resize this, and I'll go to the maximum, 31.5, resize. A couple of minutes it's going to take. It'll be done. Okay, now the partition is extended 31 gigabytes. We have all 31 gigabytes available for the Linux environment. One thing I want to mention at this point is if you choose to work with a different SD card image, it is possible that this FAT partition, when you view it through this tool or from another tool, this partition might be situated, you might find it situated next to the Linux partition, right? Maybe somewhere over here. So in that case, what you can do, you can use the gpart tool to move the FAT partition or FAT partition to the end. Then your Linux will be given the choice. You will, or in other words, you will see the choice to extend or resize your Linux partition. Otherwise, your tool will say, no, cannot extend the partition, even though your empty partition will be there and you will be able to view it, format it, whatever you want to do, but the Linux won't be allowed to resize. So just move the FAT partition all the way to the end, then your free space will be right next to the Linux, and then you can expand into that free space. So okay, so that's that. Okay, so this is our SD card. Now what I'll do is I will disconnect our SD card. Let's eject. Let's see if it safely ejects. Okay, it doesn't want to eject. I'm just going to remove it. Okay, here's our SD card. Let me make sure my video was running. Okay, I'm going to remove my demo SD card, put it safely somewhere. Okay, and let's disconnect these wires. Linux is connected. Oh, I want to do one other thing. Not sure it's booting or not. Okay, let's see. Another thing that I want to do, or I want to point out, that you see this white cable, it is connected to the UART USB connection here. And this is right now, and all of these default Linux images, you'll find that this UART is acting as a console output. So you can see my USB is connected to my laptop, and I have PuTTY open and connect. I'm going to connect to the USB 0 connection. Make sure that the frequency or the baud rate is set to 115, 200. Gonna open. Let's see what it looks like. Nothing yet. Okay, the image doesn't want to boot in this MCell configuration. Let's change the configuration. So what I'm going to do, I'm going to change this MCell configuration to 0101. So first one from the left is 0, 1, 0, 1. So it's difficult to see here, but I suppose you get the point. 0, 1, 0, 1. So let's plug it in again and watch our UART output. Okay, it booted. And this is one of the other thing I didn't understand at this point. Maybe I'll get it later. That these default images, they come with the RBF files, and they are definitely created with a option that we have available, and it is the only option that I can use to make it work. This MCell setting that you see is that I think it's a 32-bit transfer configuration. So basically the image, FPGA image that HPS transfer over, it transfers over at 32 bits. Okay, the zero, all zero position basically means that it'll be 16-bit. So when we get to that point, when we convert these output from the Quartus into the RBF files, but for now I don't get it that this option works for the supplied RBF files, but the one that I can create is 16-bit only. I cannot create a 32-bit. I'm not allowed to. Maybe it's something to do with the license, but the message clearly says it's not the license. Anyways, so we'll come to that later. Right now, we'll just move on with this. All right, the login for this image is root, and I think the password is blank. Yeah, there you go. So password is blank. Now, a couple of things I want to do is basically first prepare the SD card and and few things that I want to prepare. One of the things that I want to do is program it for a static IP address and make sure that some applications that are vital for uh, our programming and so on are present in this image. So we will do those things. Let's start with the IP address first. Okay, instead of going to the IP configuration, what I will do right now is get into a terminal mode. So I want to discard this PuTTY connection or disconnect this PuTTY connection and connect through the terminal. So before I do that, I want to know my current IP address. And my current is 178. You can see that I'm using the X notation Maybe there is a X server already present in there. We'll find out. Okay, let's see. I usually use Nautilus. Let's see, Nautilus is not present. Okay, is there a Pacman FM? No, neither is present. Okay, we'll install Nautilus for now. Let's see if we can install our Nano. Nano is just a text editor, a terminal-based text editor that I enjoy using. So I'm very familiar with it. I can, okay, as it's installing, and let me show you. Oh, it's done already. It's done. Okay, so let's go back to our interfaces and Nano interfaces. Why is it taking so much time? Ah, there we go. Okay, so this is set for DHCP. Wireless is disabled. What we want to do is add our static IP address. Let me see. There's a example out there. Ah, Ask Ubuntu. That's a very good source. Okay, we are going to just copy this piece.
I want to make sure that I'm editing the right file.
So at this point, I decided that I will not use the static IP address. Temporarily, I abandon it basically. Temporarily, I abandon the static IP address, and then I use DHCP, I changed the configuration on the Linux to DHCP, and then I updated the Nano and other tools that I was planning to use. Then I changed that DHCP configuration back into static IP address that I intended in the first place. However, I noticed that my router did not register this device. No matter what different sequence I configure this IP address with, uh, or DNS address that I found on my device, and I try to use that in this device. The DNS IP address that my router was using, I try to use that, and I try to change its sequence in the configuration file, but changing the sequence did not make any difference. The static IP address, although did allow the device to be online, but the device stayed within the local network, and it could not reach the WAN, the wide access, the outside network basically. So I just basically stuck with the DHCP for the updates, and when I was done with the updates, I changed it back to the static IP address. So in order to save the time, I'm just summarizing exactly what happened, and instead of adding more video content to this already lengthy video, a simple explanation definitely will help everybody. Okay, let's continue here, and I will start from the point where I started to develop the FPGA and other configuration aspects of the project. Okay, folks, so I have to resort to DHCP. The static IP address is not working for us, and I have tried changing broadcast and changing the orientation of the commands in the interfaces file, but it did not make any difference. So something is clashing with the IPv4 configuration. Maybe IPv6 is conflicting with IPv4. I don't know. I don't want to get into that research at this time. I want to continue, and at this time what I want to do is make sure all the tools installed in my SD image, and just continue, move forward to the next step. So let's make sure that so I've already enabled the DHCP, and I can ping outside of my LAN. I can ping the WAN, basically the Google or any other website at this point. So now what I want to do is the next step, make sure my Nano is installed, which I've already done, and all I can do is show you the installation script, output of the script, and it'll tell me that it's already installed. Oh, it was already installed. I don't know what went through again. Okay, I take it back. So it just wanted to do it again. Let me try again. Let's see what it does in the next attempt. It's already installed now. I don't understand. I'm very sure that I used this a few seconds ago. Interfaces. Oh, network interface. Let me see. Control X. Oh. What's going on? Network interfaces. This is inside the network. Yeah, there you go. So this was my static IP address. I even changed it to the one I had in my demo SD card. That didn't make any difference. I thought my router was preventing the output, the WAN traffic from this device, but that wasn't the case. And then I came down and I disabled DNS and re-enabled DNS. It did not make no difference whatsoever. So okay, but for now, okay, my Nano is installed. Let me check what other items I have to configure. And no, that's oh yeah, Nautilus. That is also installed. So I did install these two items while we are offline, and I don't know why it appears it's not there anymore. Okay, I'll install it one more time. Oh, let me take it back. I think yes, I reverted to the pack using I reverted to using pacman fm PC man FM. So yeah. So earlier I was making a mistake in the name. It's PC man FM. So this is my root in the current SD card. Nothing in the desktop right now. Applications. Let's see what's installed inside. Yes. So I can run the terminal from the file manager. So it's more like working on your desktop. It this way I can open multiple apps. For example, I can open a LeafPad editor, edit the file here, install something parallel at the same time, and yeah, this is gonna be fine. So we are ready for our next step. Folks, I have to stop this video here. The this explanation and overall issues that I came over in this whole process is a bit too long, and that's why I wanted to capture these in the previous parts in part 2 and 3. But since I started with the new SD card image, I had to start over and explain that from the beginning exactly how I achieved that. So let's pause it here, and I will continue the rest of this process in the next part. Okay, folks, see you in the next one.